So today we are going to see dry compression versus wet compression. Okay, in previous lecture we have seen what is vapor compression refrigeration system, and we had seen the cycle on pH diagram. Now we will see what are the different types of compression, and based on that what is the effect on the cycle. So here you observe we have two types basically written over here: dry compression and wet compression. Now what is meaning of this? Understand, I have shown here temperature versus entropy diagram, and this is the vapor dome. So compression process is isentropic. So here you can see 1 to 2 dash, 1 dash to 2 dash, or 1 to 2. It is vertical line in upward direction, indicating compression process of different types. So if you consider process 1 dash to 2 dash, where you observe 1 dash inside the vapor dome. What is meaning of this? At point 1 refrigerant is in liquid plus vapor state, whereas at point 2 it is saturated vapor. So at point 1 dash we have liquid plus vapor. At point 2 dash I have the whatever refrigerant is there, it will be saturated vapor. So this type of compression is called wet compression. Then observe the second compression, which is called dry compression. Now dry compression, point number 1, it starts on dry and saturated vapor curve. Okay, and point 2 is in superheated vapor region. Now because of this, what will happen? You observe over here, this is the extra area. Okay, if you consider compression from 1 dash to 2 dash, okay, and if you consider compression from 1 to 2, okay, this part is the extra area, which will, since it is on the TS diagram, it will indicate the Q, but since this compression process is part of a cycle, then that Q will result in for a cycle Q net is equal to W net, and basically indirectly we can say that that area could represent work. So for this type of compression we have some extra work, but you observe since point 1 dash is shifting towards right, it becomes 1, the refrigerating effect will also increase, because at this location somewhere, suppose we have point number 4. So if you consider 4 to 1 dash, okay, this length, so H1 dash minus H4 will give us refrigerating effect in case of wet compression. But if you consider dry compression, the refrigerating effect will be given by H1 minus H4. So if you observe this diagram carefully, the work is increasing, but at the same time refrigerating effect is also increasing. Okay. Now, why we are studying this wet versus dry compression? Understand that. First, we have talked about what is the meaning of dry and wet compression. So, if point number 1, or you can say 1 dash, is in wet region, and the point after compression is on saturated vapor curve, that is called wet compression. And if the initial point before compression is on saturated vapor, and after compression the vapor becomes a superheated vapor, that is called dry compression. Now what happens, it is desired to have in many compressors dry compression. Okay, that is point 1 is on saturated vapor curve, and the after compression point is in superheated vapor region. Now why is this? We have already talked about the effect of in the previous session, sludging. Okay, so here I had explained you what is sludging in case of suction accumulator. So here what will happen, if we supply the liquid refrigerant, okay, some amount of liquid is present at the inlet of the compressor. In that case, what will happen, liquid will get trapped. Okay, we had seen the two cases of sludging, that is when cycle is on and cycle is off, and there are chances of sludging over here. Okay, and it will damage the compressor walls, piston, cylinder, all those things. So first effect of wet compression will be sludging. Okay, it will be prominent in reciprocating compressor, but there are different types of compressor. So if we are using some other type of compressor, it might happen that the liquid sludging, the effect of sludging is not prominent in that type of compressor. Then second is the liquid refrigerant droplet may wash away the lubricating oil. Okay, so here you see at the inlet of the compressor I have liquid plus vapor. So that liquid part, it will wash away the lubricating oil which is present between the piston and the cylinder, and it will increase the wear. So these are some of the disadvantages of wet compression. So it is desirable to have dry compression. Now it could be possible that in some cases wet compression is also important. Okay, so we will see what are those cases. So therefore it is desirable to have dry compression with vapor initially dry saturated at 1, meaning this blue color point 1, or even slightly superheated if reciprocating compressor is used. So either point 1 or 2, this process can be a dry compression process, or it can also be like point 1 is in superheated region and point 2 will always be in superheated region. Okay, it depends actually, but if point 1 is a dry saturated vapor, always point 2 is superheated. Same way, if point 1 is superheated, then always point 2 will also be superheated. Okay, because you have to see the nature of this TH diagram or pH diagram. So here what I can say that I can, for reciprocating compressor, we should always have dry compression, that is point 1 should be on saturated vapor curve, or you can also say that point 1 initially itself it is superheated vapor. Okay, now what happens because of this? There is increased work in the cycle. So there is increased work of cycle due to substitution of wet compression by dry compression, which appears as the area. So here area has been shown 2 2 dash 2 double dash. Now this area is called superheat horn. Now we will talk about in which case the dry compression is desirable and in which case the wet compression is desirable. Okay, so here you observe wet compression is in some cases is indeed desirable and also practicable with the use of a continuous flow machine like centrifugal or a screw compressor. Now this type of compressors, especially the centrifugal compressor, it is used for very large chillers. Chiller meaning central AC. Okay, central AC has number of parts. So the part which is responsible for the cooling effect of the water. Okay, there what happens in central AC? We have three refrigerants basically. Okay, main refrigerant, whatever is being used, it chills first water. Then that water is sent to the different locations inside the building, and that in turn chills the air with the help of air handling unit. So in very big tons of the central AC, centrifugal type of compressor is used. Okay, and in medium or maybe small system, screw type compressor is used. So in these types of compressor, there are no walls. Okay, so effect of sludging is not prominent over there. Okay, it will not damage the piston walls because the piston cylinder arrangement is not present. Okay, so that is why in case of centrifugal and screw compressor we can use wet compression. But if we have reciprocating compressor, in that case we have to use dry compression, or maybe point 1 can be superheated also, that is entry to the compressor. Now we will see that this analysis is now very important. It could happen that in wet compression in some cases COP increases. In case of dry compression sometimes the COP depends. Okay, in case of sometimes in superheating also COP decreases. So it depends on the type of refrigerant. Okay, how we will see in shortly. Now here same thing is written, there is improvement in COP with wet compression in case of ammonia. Now this is a special case. Okay, if you see some other refrigerants, it might happen that because of the wet compression the COP might reduce. But for ammonia wet compression is desirable. How we will see, okay, after some time. What is the reason behind that, that also we will see. So in case of ammonia, wet compression will result in improvement of the COP, meaning we have to compress, initial point will be in wet region and the final point after the compression will be on saturated vapor curve of the refrigerant. Now we will see some example, okay, of dry and wet compression. Okay, so before that what I'll do, I'll go to one more topic. We will discuss the pH diagram, the effect of superheating. Okay, now you have to observe over here. This is very important slide. Okay, important from Viva point of view also, so understand this properly. So here you observe the effect of superheating. Now superheating, it is done in which component? Compressor. So we are going to talk here. You observe on pH diagram, 1 to 2 process is isentropic compression, 2 to 3 is constant pressure heat rejection, 3 to 4 is isenthalpic throttling, and 4 to 1 is constant pressure heat absorption in evaporator. So since we are going to talk about superheating, we are only going to talk about process 1 to 2, which is compression. So you observe over here, this is 1 to 2 compression, which is dry compression. Why? Because point number 1 is on dry saturated vapor and point number 2 is in superheated region. Same way you observe point 1 is superheated to 1 dash and 2 dash is also superheated point. So what is the effect of superheating? Whether the COP will increase or COP will decrease in case of vapor compression refrigeration system, that effect we are going to see. Okay, now you observe over here closely, when we have cycle like this. Okay, now third case will be what? It is irrelevant to superheating, but third case could be wet compression like this. Okay, so all three cases we can evaluate over here. Suppose this is 1 double dash and 2 double dash. Okay, so here we have 1 to 2 dry compression, 1 dash to 2 dash means point number 1 is superheated initially before the refrigerant enters the compressor, and point number 1 double dash to 2 double dash, it indicates the wet compression process. So I am going to explain all the three cases over here. Okay, first we will focus on dry compression and the point 1 is initially superheated. Okay, so 1 to 2 and 1 dash to 2 dash, that we will see. So here you observe, initially when process is 1 to 2, what is the refrigerating effect? H1 minus H4, this is the refrigerating effect. But when I talk about the process 1 dash to 2 dash, meaning superheating is done. Okay, so where is that superheating done? In the evaporation process only. Here you observe 4 to 1 dash, that is evaporation process. So in evaporation process itself the superheating is done. Okay, now there are different types of superheating also. One is useful superheating, second one is useless superheating. Okay, what are these we will see later on. So 1 dash to 2 dash process is the superheating, meaning point 1 is superheated to the entry to the compressor. Now you observe here H1 dash minus H4. Here you observe the refrigerating effect has increased, whereas if you consider the second thing, that is the work consumed by the compressor, you observe for the initial cycle, that is 1, 2, 3, 4, there the compression work is H2 minus H1. And when I consider the second cycle, that is the effect of the superheating, that is cycle 1 dash, 2 dash, 3 and 4, what is the compression work? H2 dash minus H1 dash. Now it is clearly visible over here that due to superheating, okay, that is the inlet of the compressor, we are changing the point from 1 to 1 dash. In that case, it is clearly visible over here that always the refrigerating effect is going to increase. So refrigerating effect is increasing from H1 minus H4 to H1 dash minus H4. So this refrigerating effect is always increasing. Now if you observe the work, okay, compression work, H2 minus H1, this is the compression work. Now the nature of the isentropic lines, these are slightly diverging in nature, okay, on pH diagram. So here you observe this H2 dash minus H1 dash, that is also greater. Now it depends, see what happens here, there is increase in refrigerating effect, also there is increase in work. Now what is COP? COP is refrigerating effect upon work consumed by the compressor, or you can say power consumed by the compressor. Now here the issue is refrigerating effect is also increasing in case of superheating. Okay, we are not talking about right now wet compression, we are just talking about the process. Initially it was 1 to 2 compression process, and then because of superheating it is 1 dash to 2 dash. So because of superheating, refrigerating effect is increasing, compressor power consumption is also increasing. So now it depends, COP may increase or it may decrease. Okay, now here there is mistake in RS Khurmi. If you see RS Khurmi, it will say that the COP decreases. Okay, so here you need to be careful that because of superheating, the COP may increase or decrease. How we will understand in detail. Okay, now because of this, what happens? We also have specific volume lines. Okay, on pH diagram, what are the nature of those lines? I'll show you. Okay, here I'll zoom this part. You observe here, I have shown this constant volume curve. Okay, now these dotted lines, here you observe these are the dotted lines. Can you see this dotted line दिख रहा है सबको? हाँ, these are constant specific volume lines. Now observe the value. On the upper side, this value is 1 meter cube per kg. If you see this value, this is 1.5 meter cube per kg of specific volume. Meaning, as we are moving in downward direction, here you observe specific volume is increasing. And because of superheating, now let me go back to the previous slide. Now, because of superheating, if I consider for point 1, this will be the specific volume curve. But for point 1 dash, since it is towards right, this will be the specific volume curve, and the specific volume increases in downward direction. So if so suppose this is V dash, so what will happen? The specific volume is increasing from V to V dash. So because of this, what will happen? What is specific volume? Volume per kg. Okay, what is the volume of refrigerant which is entering the compressor? Now since the volume is increasing, the size and the cost of the compressor will increase because of the superheating. Next thing, what the superheating does is, superheating ensures that always there is vapor at the entry of the compressor, because point 1 is dry saturated vapor. Okay, and when I am talking about the superheating at the entry of the compressor, it means that always point number 1 is dry. It means that there is no liquid present in the refrigerant. What is meaning of that? That the life of the compressor will increase, because what if the liquid is present and the compressor is pressurizing it, and if the liquid refrigerant is incompressible, then definitely there will be much rise in the pressure inside and it might damage the compressor. Okay, so that is why superheating ensures vapor at compressor inlet, thereby increasing the life of the compressor. This point you can say that it is valid for reciprocating compressor. Okay, now there are two types of superheating I have talked over here. That is, one is useful superheating, other is useless. What is meaning of this? We will see this. Okay, so in order to explain this, I have to go to the basic diagram of vapor compression refrigeration system. Okay, now what happens if you observe this vapor compression refrigeration system? Okay, at the inlet of the evaporator, we have liquid plus vapor refrigerant, and at outlet there are two possibilities. Okay, one, we can get either saturated vapor or we can get superheated vapor. Okay, now that is called, this superheated is called super effect of superheating, what we are studying right now. Now what will happen? Suppose at the entry I have liquid plus vapor. Okay, and suppose the temperature of refrigerant over here, okay, while entering is -18 degrees Celsius, for example. Now at exit, suppose I am getting all the vapor and the temperature remains same -18. Means whatever refrigerant is coming out at this point, it will become saturated vapor. Why? Because liquid plus vapor is in vapor dome and saturated vapor, both the temperatures are same, meaning this is condition of saturation. But sometimes what happens, uh, in this case there will be what? Latent heat will be absorbed by the refrigerant from the surrounding product or from the human being. Okay, now in case of superheated vapor, what will happen? In this evaporator itself, along with the latent heat, the sensible heat is also being absorbed. Why? Because you observe what is the temperature over here, -18, but for food product to be in equilibrium inside the evaporator, it might be at higher temperature also. So what will happen? Further the heat will be absorbed by the refrigerant. Okay, and that case will be sensible heat will be absorbed. Now because of this, what will happen? The temperature will increase of the refrigerant. So from -18, maybe it increases suppose to -15. Now this is called superheated vapor. Please remember, okay, when we are talking about superheating, it's not that above 100 degrees Celsius. Okay, it is above the saturation temperature. Here, what is the saturation temperature? Minus 18. So below minus 18 means minus 19, minus 20. That will be what? That will be subcooling. But here definitely it will not be subcooling. Okay, it is being heated. It is further taking the heat. So there will be increase in the temperature. So minus 15 will be the superheating case. Now this type of superheating which occurs inside the evaporator is called useful superheating. Now what happens, sometimes this is not the case. What happens, there is not sensible heat being picked up by the refrigerant. Okay, this is saturated vapor only at the exit. But sometimes the line from the evaporator to the compressor is not insulated. This line should be insulated over here. If this is not insulated, what will happen inside the whatever refrigerant is there, its temperature is minus 18 degrees Celsius. Outside atmosphere is at 25 degrees Celsius. So this refrigerant inside will pick up the heat from the atmosphere. Okay, and because of that, this maybe minus 18 will become, suppose for example, minus 10 degrees Celsius. So there is superheating over here, and this type of superheating is called useless superheating. Okay, did you understand the difference between useful and useless? यूजफुल तो अंदर होगा ना, जो फूड प्रोडक्ट है उसमें से ही वो हीट ले रहा है, दैट इज यूजफुल. Whereas if the refrigerant is taking heat from surrounding because of if the insulation is not present over here, okay, that is why you always observe in AC or in AC na one line is insulated. Okay, you observe from evaporator to compressor na that line is insulated to prevent this useless superheating of refrigerant. Okay, next part we will see now. Continue. We will continue with the superheating case. Now, as I had told you before, for some refrigerant, COP might increase or COP might decrease because of the superheating. What are these refrigerants? Okay, now you observe over here for R12, R502 and carbon dioxide. Superheating results in increasing COP. Whereas if you consider ammonia, R22, R11, because of superheating, COP decreases. Now, why is this? We have to understand that. So, basic answer is it depends on compression work. Okay, now how? Understand it. This is very important now. You observe this is R12 and this is ammonia. Now, R12, see the slope of isentropic curve. This is isentropic curve. Whereas if you consider ammonia, just observe the slope of isentropic curve. This is the slope. We are basically comparing two pH charts, pressure versus specific enthalpy charts. One is R12 and second one is ammonia. So now tell me which slope is greater and which slope is smaller. Which slope is smaller? Huh? R717, here the angle is what? Less, meaning here basically the slope is less. Whereas if you consider R12, here the slope is more. Now if you consider compression process, you take any 2 points. Suppose this is point 1, this is point 2, this is compression process. Whereas if I consider the same distance, x distance over here, okay, and if I consider this is point 1, point 2, what do you think? In which case H2 minus H1 will be greater? In case of R12 or in case of ammonia? In case of ammonia, why? Because ammonia lines, ammonia's isentropic curves are more flatter. What is meaning of this? Between the same horizontal distance, okay, this inclination, here you observe the inclination, here inclination is what? Like this, it is more. So here basically this delta H, so basically what I am trying to suggest is compression work in ammonia is greater. So that is why if I am doing the superheating in case of ammonia refrigerant, okay, here same thing is written. In case of ammonia, superheating decreases the COP. Why? Because there what happens? Compression work will be more. But in case of R12, we just now observe that the slope of isentropic curve on the pH chart is more, meaning the compression work will be less. So that is why the superheating will increase the COP in case of R12. Now what we will do, we will try to actually understand this logic. ये क्या होता है? We will see this on a software. Now that software which we are going to see there, we will consider uh, the wet compression also, so that we can compare at the same time wet compression, dry compression, the superheated effect of superheating, as well as we will compare two refrigerants, R12 and ammonia. So this activity we have to do now. Okay, so let me go back to the software. The software name is CoolPack. You will be having an assignment also on that software. Okay, so this is the software. This is free software. Now, when you observe over here, there is one symbol over here. You have to double click on this or single click on this. Okay, now I'll take certain values. There is a criteria which is called Ewing-Gosny criteria. Okay, what is this Ewing-Gosny criteria? If COP of saturated cycle is greater than TE upon T2 sat minus TE, it means that maximum COP occurs inside the two-phase region, meaning in case of wet compression, there will be maximum COP. Okay, and if we are going for superheating, then the COP will reduce if this criteria is satisfied. So if you observe this, a pH diagram has been shown where I have shown a wet compression, a dry compression, and a case of the superheating. Okay, in case of compressor inlet and compressor outlet as well. So here we have number of refrigerants: ammonia, CO2, R11, R12, R22, R502. Okay, now here the same things are written: COP, SAT, TE, T2E, TE. Okay, so this is COP SAT, and the equation of COP SAT is this one. So if you observe for ammonia, what is the COP SAT? COP SAT means, if I consider, okay, I'll show this with the help of blue color. If I am considering ammonia refrigerant, and if I consider standard vapor compression refrigeration system, meaning point 1 is dry saturated and point 3 is point 1 is saturated, dry saturated vapor, and point 3 is saturated liquids. If I am considering this cycle, okay, whatever its COP I am going to find out, H1 minus H4 is refrigerating effect upon H2 minus H1, whatever this value I get, that is called COP SAT. So that is this value 4.77. Now second thing is, observe this equation, TE upon T2 sat minus TE. Now what is this? Understand. Okay, TE is the evaporator temperature. So this temperature, okay, here this will be the temperature, nature of constant temperature line. Okay, this will be nature of constant temperature line. This will not be the part. Okay, so in subcooled region it is vertical, in vapor dome it is horizontal, and in vapor region it is curved like this. So this is the constant temperature line on pH diagram. We have already seen the nature of this line. Okay, so for 0.4 and 0.1, whatever temperature we have, this will be T low temperature. Okay, and this is basically the TE temperature. Now what is this T2 sat? Okay, it will be the temperature of this point. Okay, point after compression. So if I draw a constant temperature line over here like this, okay, this whatever temperature is there of 0.2, that is this T2 sat temperature. Did you understand? Okay, I am repeating again. COP sat is H1 minus H4 upon H2 minus H1. This is COP sat. Then what is T2 sat? After compression, whatever point is there, its temperature. We have to convert in Kelvin, that is T2 sat. And this is the equation where if if COP sat is greater than TE upon T2 sat minus TE, then wet compression will result in giving maximum COP. This also part we are going to see on the software. So basically all the three cases we will see, and here you observe, in case of ammonia, we get that COP sat is greater than this equation, this value. That is why here you see maximum COP is yes, meaning the maximum COP we get in case of wet compression for ammonia. But if you see the second case, okay, कौन सा case है? Let me show you. In the case of R12 refrigerant, in case of R12 refrigerant, you observe COP sat value which is 4.7 and you observe this equation value which is 4.87, meaning COP sat is less than this value. It means that we don't get, okay, here it is written as no, meaning we don't have maximum COP inside the vapor dome. Did you understand this point? Now this we will see with the help of some example using the software. So I'll go to the software. What are the conditions given here? Uh, T high or T condenser temperature is 303 Kelvin and T low or T evaporator temperature is 258 Kelvin. Now I will get these values in degree Celsius. What is 303 Kelvin? It is how much? 30 degrees Celsius. Okay, so here this Tc will be 30 degrees Celsius. What is Te? 258 Kelvin. What is 258 Kelvin? How many degrees Celsius? Minus 15 degrees Celsius. Okay, so Tc will be 30 degrees Celsius and Te or T low I can say it will be minus 15 degrees Celsius. So I'll go to the software. Now we will compare ammonia and R12. Okay, so let me go to the software part. You understand how to use software because this software is there in the practical session and assignment. Okay, आपका assignment कैसे रहेगा vapor compression में? You have to solve the same question of assignment using analytical method and same problem you have to solve by software. And दोनों के PDF को merge करना है आपको. Assignment का PDF you will scan. इससे जो from the software whatever you are getting the PDF that you will merge with the theory PDF and that you will upload as an assignment. So we are using certain modern tools also. Okay, whatever we are going to solve by hand, we are comparing that with the software and that will be the part of your assignment. तो assignment में दोनों आएगा, manual method as well as software method. So understand it. So I'll go to the software now. You observe over here. I'll close this window. Okay, this is the CoolPack software. You have to left click on refrigeration utilities. Okay, now here you observe different charts are shown. Okay, so first chart is pH chart. So I'll click on pH chart and I will select ammonia which is R717. So here you observe we have ammonia R717, then click OK. So this is the chart of ammonia refrigerant, pH chart of ammonia refrigerant. What I am trying to prove over here, I am trying to prove this point which is there in the presentation. What is that point? This one. In which case the maximum COP occurs inside the vapor dome. So for ammonia it will occur, for R12 it is not going to occur. That point we are going to see over here. Okay, that is my objective. So for ammonia what I'll do, I'll go to this cycle part. Okay, what is the evaporator temperature? Minus 15. What is the condenser temperature? 30. Only this much I have to do and I'll click draw cycle. So that cycle is now drawn on pH chart. Now I'll go to this red color part which is show info. So you observe over here what is the COP value which I am getting. This is COP sat. Okay, this COP sat is 4.78 for ammonia. Same thing is given in the presentation. Okay, you confirm it. Can you see this 4.78 we got from the software? Here that value is 4.77. Did you understand? Now what we will do, we will try to find what is this T2, what is this TE upon T2 sat minus TE. For that we require T2 sat value which is this temperature. So how to get this temperature from software, understand. So what I'll do, I'll go to coordinate points. Okay, I'll go to coordinates points and I'll find here the maximum temperature. Okay, so you observe for point number 2 what is the maximum temperature? 98.417 degrees Celsius. Now convert this to Kelvin. Please tell me what is the value? 98.417 degrees Celsius to Kelvin. कितना आ रहा है Kelvin? हाँ, so 371.41. Let me go to the PPT. See, 371.41, here this value is 372. Did you understand how that T2 sat value is taken? It is basically of this point. So this is matching. Now what we will do, You have to just simply substitute in that equation. T2 sat we know T is how much, 258. So you will get 2.26. It means that for, since COP sat is greater than this equation, it means for ammonia maximum COP will occur when we are doing wet compression. Now this we will prove from the software also. Okay, let me go back to the software. So in the software, I have shown already one cycle. Okay, here you can see cycle number 1, which is for the standard vapor compression system, where we have 1 to 2 as dry compression. Now what I'll do, I'll draw one more cycle. Okay, so again I'll consider the same evaporating temperature, which is minus 15. Then condenser temperature is how much, 30, and the superheat value, okay, I'll reduce it so that I get wet compression. Okay, so here you observe point 1 is in wet region and point 2 is approximately on dry saturated vapor curve. Okay, now what I'll do, I'll compare the two cycles. First cycle was dry saturated, second cycle is wet compression. Okay, third also I will draw superheating. Okay, so I'll go over here, I'll consider evaporator temperature, that is lower temperature, I'll keep it same, minus 15. Condensing temperature, suppose I am keeping it same, 30. Okay, what I'll do, I'll increase the superheating of this point. Suppose I'll keep that superheating as 10, तो ये temperature line जो है यहाँ तक आएगा. This is 10 degrees Celsius, so point number 1 will be at this location. Now you observe. Okay, I'll change this to degrees Celsius and I'll keep this as 10 degrees Celsius and I'll draw cycle. So you observe over here, this is the constant temperature curve. Wherever it cuts the constant pressure horizontal curve, there I am getting 0.1. So I have drawn here, this is cycle number 1, which is standard vapor compression cycle. Then cycle 2 is having wet compression and cycle 3 is having superheated compression. One more cycle I'll draw over here. Okay, I'll increase the superheating. So evaporator temperature I'll keep minus 15 only. Condenser temperature I'll take 30 and superheat I'll increase. Okay, I had taken it 10, now I'll take 20. So the point will shift at this location now. Okay, so I'll take this superheating as 20 and I'll click draw cycle. Okay, now observe, this is the point, fourth cycle, where I have superheating of 20 degrees Celsius. So I have drawn 4 cycles now. I'll go to cycle info. Now closely observe the COP. For first cycle, which is having dry compression, what is the COP? 4.78. Okay, now I'll note the COP at the same time on the screen. For dry compression, what is the COP? 4.78. Okay, second cycle which I had shown was which cycle? Having wet compression. So I'll go to this one. Observe the COP. What is the COP? For wet compression, the COP has increased. What is that value? 5.63. Now if you consider 10 degrees Celsius of superheating at inlet of the compressor, that is cycle number 3. For cycle number 3, what is the COP? 4.52. So for superheating case 1, okay, the COP is 4.52. And for the last cycle where I have superheating of 20 degrees Celsius, okay, that is cycle 4, what is the COP? 4.44, meaning superheating is decreasing the COP for ammonia. So for this one, the cycle 4, what is the COP? 4.44. So you closely observe over here what conclusion we are getting. For ammonia, wet compression, which is this is the wet compression, I'll show this is the wet compression. What is the COP? 5.63. Now if I consider dry compression, what is the COP? 4.78, means COP has decreased. Next, I'll consider 10 degrees Celsius of superheating. This is the superheating of 10 degrees Celsius. What is the COP? 4.52. It has further decreased. Then I'll take the next case, further superheating to 20 degrees Celsius. Again you see the value for the fourth cycle, it is decreasing, meaning from wet compression, if we are increasing Okay, if you are going if you are shifting the compression point 1 towards right side, the COP is decreasing for ammonia. Did you understand this analysis? Now take screenshot of these values. Okay, we will now see for R12 refrigerant, where in the same way here it is decreasing, for R12 it will increase. Okay, so what you do, you take photo of this so that you have some reference or screenshot of this. Now what I'll do, I'll clear everything over here and I'll change the refrigerant. Okay, let me close this. Okay, I'll minimize this, go back to the CoolPack. Okay, I'll click refrigeration utilities and I'll select pH chart and R12 refrigerant. Okay, so this is R12. I'll click OK. Now I will maintain the same temperatures. So I'll go over here in cycle. Evaporator temperature was -15, condenser temperature is 30. I'll draw the cycle. So this is the first cycle. Second cycle is wet compression. Okay, so I'll keep same evaporator temperature -15, condenser temperature 30, and superheat value I'll change so that it becomes uh, wet compression, and I'll draw the cycle. So here you observe the second cycle it is wet compression. Okay, now I'll go to I'll draw certain superheat. Let me check how much superheat I can show. I'll show for 10, it will come over here, and then I'll show for 20, which will point 1 will come at this location. Okay, so I'll go over here, then this is -15, condenser temperature is 30, and superheating is 10 for first case. So this is third cycle. Okay, here you see wherever this 10 degree Celsius line intersects with constant pressure horizontal line, that will be inlet point to the compressor point 1. Same way I'll increase the superheating to now to 20 degree Celsius. So the point will shift at this location. So condenser evaporator temperature is -15, condenser temperature I'll keep same 30, and the superheat value I'll increase to 20 degree Celsius. So I'll get fourth cycle. Now we will analyze this cycle. If I go to cycle info, observe the first cycle, which is dry cycle. Okay, again we will do the same activity for dry compression, which is from this point to this point. What is the COP? 4.7. 4.7. For wet compression, cycle number 2. Okay, for this will be 0.2. So for wet compression, I'll select cycle 2. What is the COP? 4.7 only. So for wet compression, the COP has not changed. Okay, it is remaining 4.7 only. See, for every refrigerant it could be different because it depends on the property of refrigerant from pH chart. Okay, then third cycle I'll consider the superheating one. This will be cycle number 3, where I'll consider superheating cycle number 1. So what is the COP? Now for R12, that COP should increase. So we will confirm it over here. Okay. So if I select cycle 3, what is COP? 4.74. So slightly the COP has increased. 4.74. Now I'll consider the last one, the 20 degree Celsius superheat point. Fourth cycle. Okay. So for fourth cycle, what is the COP? It will be S2. For fourth cycle, see the COP value, it is 4.77. So initially it was 4.7 for both wet and dry, and when I'm increasing the superheat at the entry of the compressor, you see the COP has increased 4.74, then 4.77. Meaning for refrigerant like R12, superheating increases the COP. Now did you understand the comparison? Okay. So you take the screenshot of this also, and you compare it with the previous screenshot which you have taken. Okay, for ammonia what you have taken, and for R12 what we have taken. So you can compare the values. Okay, so same thing is written here. We'll go back to the presentation. Okay, so for ammonia, since COP sat is greater than this value, the maximum COP is yes, meaning the maximum COP occurs in case of wet compression inside the vapor dome. And for R12, since COP sat, we had got that value as 4.7. You can check the screenshot. Okay, so that value is less than this value. So that is why maximum COP does not occur, no, in the vapor dome. Okay, so I hopefully you have understood this Ewing-Gosny criteria.